thanks for watching, and our goal for today is to derive the heat equation, ut equals duxx. And I would like to remind you of the physical interpretation. So here, U of xt, what it measures is the temperature of a metal rod or metal string at position x and time t. So in other words, if you have an infinite metal string and you're at time t, and you want to figure out how hot is this point x, well, the answer is U of xt, which gives you the temperature. Now, it is possible to derive the heat equation using physical principles such as Fick's law, but instead of what I'm going to do, I'm just going to derive it from scratch using elementary principles. Because what is heat? Heat simply results from particles bouncing back and forth. Imagine, for instance, rubbing your hand and it gets hot. It's because your skin particles are rubbing against each other. So once again, heat results from particles randomly moving around. And I'll give you a couple of pictures illustrating that. For instance, if you have a hot gas, you can think of it as a bunch of particles that just randomly bounce back and forth. Like this one is going this way, this one is going this way, etc., etc. So that would be a hot substance. But something that's not hot, think like an ice crystal, usually has this structure where we have a bunch of atoms that don't move around at all, that are just static. So once again, this would be heat, and this would be no heat. And it's in fact, in terms of those random particles bouncing around, that we will derive the heat equation. So first of all, we won't really talk about temperature here, but rather the concentration of particles, because the particles are randomly bouncing around. So if there's more of them, that part of the rod is a bit hotter. So let U of xt really be the concentration of particles at position x and time t. And time t. And really, what we want to figure out in order to derive the equation is what happens if you change x a little bit. So if you move a little bit to the left and to the right, and also change time a little bit. Like think increasing by a millisecond. So question, what happens as we change x and t a tiny bit? And by the way, this should remind you a bit of the savings model in your ODE class, because we had the same issue. To figure out our savings, we just want to figure out what if we wait a little bit of time and see how our savings changes. And it's the same thing here. So just a little bit of notation. So h is a change in position. So h is delta x, which is change in x. So let's say we move by 1 nanometer to the right. And tau, which is delta t, which is the change in time. So let's say we wait a millisecond and see what happens. Now, extremely important for the end, so please remember this. Tau will be to be announced. And in fact, what we'll do, later on, we will choose tau in terms of h to solve a problem. It seems very strange, but this is an example of what's called a phenomenological model, meaning that let's adjust our parameters to get a very interesting differential equation. And the reason for this is, well, by choosing h and tau, we have 2 degrees of freedom. But it's enough just to have 1 degree of freedom, 1 parameter. So it's actually okay here to choose tau in terms of h. Both of them will be small, I promise. And now what we want to consider is a very small neighborhood of x. So let's fix x and consider a small interval around x. So consider a small interval. In this case, I'll explain why. X minus h over 2 and then x plus h over 2 around x. So here we have x, and then, well, this is x plus h over 2 and then x minus h over 2. First of all, why h over 2? Because the total length, we want it to be h. I'll simplify our formula very soon. And more importantly, why are we considering an interval and not a point? Because at this point, there might be no particle or 1 particle, because it's a single point. And it makes more sense to consider the neighborhood of that point, because there might be many particles bouncing around. And also, this is what allows us really to go from concentration to number of particles. Because remember the formula for concentration in chemistry? So concentration, well, technically it's mass over volume. But here we have a one-dimensional thing, so the analog of volume is length, and the analog of mass here is number of particles, because the more particles, the heavier things are. Number of particles. And what's nice is we know the concentration, we know the length, so I can actually tell you exactly how many particles are in that interval. So the number of particles, that is the concentration times the length, which ultimately gives us, so the concentration is u of xt, and the length is h, so that's just u of xt times h. In other words, to figure out how many particles are in that interval, well, you just take the concentration and multiply it by h. And this will be very useful for what's to come. So just to recap what we talked about so far, the number of particles so in that interval, so let's just call it around x, is h times u of x. So remember, whatever u we have, we just multiply by h. Because also it's a small number of particles, because the interval is small. And so far what we've done, we just focused sort of at x. And the next goal is to look at the interactions between the neighbors of x. Because remember that the particles, they bounce around. So step 2 is really look at the neighbors of x. And really what we want to do now, we want to take the rod, and maybe this is x, and we want to divide it up into those small intervals, right? So this is a small interval of length h, and then we have the neighbor, x plus h, and we want to divide this up also, and then x plus 2h, etc., etc. So that's sometimes called a partition. We want to partition the interval into those little neighborhoods. X minus h, and x minus 2h, etc. So once again, what have we done here? So divide up the rod into small neighborhoods. That's of x. Think like little countries, and we want to figure out how the particles jump from one country to the next. Now, here is the most important assumption that we'll do now, which is really what makes the heat equation work. Well, our assumption is we assume that particles randomly jump to the left and to the right from one region with the same likelihood. So if you're in this region of x, the chance you move to the left is 1/2, the chance you move to the right is 1/2 as well. So once again, to recap, main assumption, the particles randomly jump to the left, to the left, to the left, or right, with the same probability. So once again, just to recap the picture, well, we have x, and we have the neighborhood x plus h, and x minus h. So the chance that you move to the left is 1/2, and the chance you move to the right is also 1/2. Now, to derive the PDE, what we want to do, we want to calculate the change in the number of particles in 2 different ways. So step 3. Okay, so calculate the change in particles in 2 ways. Here's what I mean by that. Because on the one hand, to figure out how the number of particles changes, it's the number of particles in the future minus the number of particles in the present. Just like for the savings model, it's your savings in the future minus the savings you currently have. So on the one hand, and that's what's called a temporal change. So change is just future minus present. Now, what does future mean? At time t plus tau, and present is at time t. So the present number of particles, remember it's h times u of xt. And the future number of particles, it's the same thing, but at time t plus tau. on the one hand, that's sort of the easy step. And now, using our main assumption, let's figure out what happens actually during that time. So just to recap, we want to figure out the change in the number of particles. Of course, one way is to say it's the number of particles in the future minus the number of particles in the present, but it tells us nothing about what's actually happening. So now what we want to do, we want to calculate the change in a different way to really reflect the dynamics of the situation. So, on the other hand, well, you can actually think about this in terms of the chemical tank problem in your ODE class. Because the change is also the same as the number of particles going in minus the number of particles going out. So number of particles going in minus number of particles going out. So it's the famous in and out equation, not to be confused with the delicious burger place. And so let's just calculate the number of particles going in and the number of particles going out based on our model. So first of all, what are the two ways of going into region of X? Well, either you can go from X plus H and jump to X with probability 1/2, or you can go from X minus H to X also with probability 1/2. So the two ways of jumping into X are either from the right or from the left. And so in would be particles from the right and then plus particles from the left. Now, how many particles are there from the right? Well, first of all, it's at X plus H. So you X plus H presently. Now, remember, to get the number of particles, you multiply by H. And because half the particles move from the right, we have to multiply this by 1/2. So 1/2 H U of X plus HT. And then from the left, it's the same thing except with X minus H. X minus H. So this is in, and now let's see what's out. Well, for out, there's really two ways of thinking about this. So we have X, X plus H, X minus H. What are the two ways of going out of X? Well, either you go to the left with chance 1/2 or to the right with chance 1/2. So out means out to the left plus out to the right. And again, what is that equal to? So we're focusing on X. So U of X comma T. To find it in particles, we multiply by H. And then with chance 1/2, those particles go to the left. And with chance 1/2, those particles go to the right. That is one way to interpret this. Or you can simply say, well, all the particles at X move out. So it's actually the same thing as hu of xt. Kind of neat how the math checks out here. Perfect. So that's all we needed. So now we can actually calculate the change. So if you combine both things, so change is in minus out, which once again was h over 2 u of x minus h t plus h over 2 u of x plus h comma t, and then minus out, so u of xt. Which, if you want, you can combine this into h over 2 u of x minus h t minus 2 u of xt plus u of x plus h comma t. Very good. So this is sometimes called the spatial change. And now we just need to combine this. Let's combine future minus present with this to ultimately get our PDE. So here's where the spicy things happen. All right, so I think it's step 4. So now let's just combine. So on the one hand, we had our business of future minus present. So h u of x t plus tau minus h u of xt. So that's future minus present. And we found out this is the same thing, if I'm not mistaken, as h over 2 and then u of x minus h t minus 2u of xt plus u of x plus h, comma. Or maybe switched around, I don't quite remember. But one thing already, what's nice about this is we can cancel out the h, and then we really end up with u of x t plus tau minus u of xt equals 1/2 u of x minus ht minus 2u of xt plus u of x plus ht. And well, let's look at this a little bit, because here's where the calculus kicks in. Because, ignore the x for a second, we have u of t plus something minus u of t. What does it smell like? Well, kind of smells like derivatives. But in order for the derivative to appear, we need to divide both sides by tau. So you divide this by tau, you divide this by tau, so 1 over 2 tau. That's first of all. And then, you will see this in a second, but this actually looks like a second derivative term. But in order to make the second derivative term appear, what you have to do, you have to multiply top and bottom by h squared. So divide this by h squared, and in order to get a balance of equations, you multiply this by h squared. All right, very good. And now, all you need to do is to take the limit as tau goes to 0 and as h goes to 0. So, first one note, so if you take the limit as tau goes to 0 of u of x t plus tau minus u of xt over tau, once again, if you ignore this x, it's just a limit in t. And this precisely should go to the t derivative of u. So by definition of a partial derivative, that should be ut xt. That's on the one hand. On the other hand, as I mentioned, this term will go to the second derivative. And as I said, the limit as h goes to 0 of this term, so u of x minus ht minus u of xt, so 2u of xt plus u of x plus ht over h squared. This turns out to be uxx at x. And how come this is true? So you may or may not have seen this. I just want to quickly show this to you. Well, if you ignore this time the t, and you take the limit as h goes to 0 of f of x minus h minus 2f of x plus f of x plus h over h squared, then either you can Taylor expand, or if you find that easier, you can apply L'Hopital's rule. So this is the limit as h goes to 0. So you differentiate this with respect to h. So what you end up getting is f prime of x minus h times the derivative of x minus h with respect to h, which is minus 1. This doesn't depend on h, so it becomes 0. And then same spiel here, we get f prime of x plus h times 1, and this over 2h. And then you just repeat it once more. So this, by L'Hopital's rule, is the limit as h goes to 0. And now f double prime of x minus h, and once again, times minus 1. But we also have this minus 1. And then same thing here, f double prime of x plus h times 1 times 1, and this time over 2. And in the end, what we end up getting is, that becomes f double prime of x minus 0, and then times 1, plus f double prime of x plus 0 over 2. So that's 2f double prime of x over 2. And that's f double prime of x. So in fact, it makes sense that it goes to the second derivative. And so in the end, in the limit, our equation becomes simply ut equals to this weird limit. So limit h and tau goes to 0. And then that becomes, I believe, h squared over 2 tau, and then uxx, which is the heat equation, except what in the world is this? And strictly speaking, this limit can be anything, because this could blow up, this could go to 0, this could go to a concrete number. Well, I don't know if you remember, but at the beginning I said, very important, tau is to be announced. Now is where we'll announce what tau is. So in particular, let's choose tau to get an interesting limit. So step 5, grand finale. So choose tau such that h squared over 2 tau equals d for some d. And once again, this is a phenomenological model. We want to choose our parameters to get an interesting limit. So in particular, what we get is, in this case, tau is h squared over 2d. This is all in good. The only thing we need to worry about is whether tau is small, But notice, as h goes to 0, tau also goes to 0. Then, as h goes to 0, tau goes to 0 as well. So, strictly speaking, what you would have to do, you would have to repeat the proof from the very beginning, and you would say, let h be small and tau be h squared over 2d. Then everything is in terms of h, and in the end, you would just let h go to 0. Because as h goes to 0, this will go to 0, and everything else in our equation is still true. And so what we obtain in the end, what we get is ut equals to that weird limit times uxx. But remember, we chose tau so that that weird number is always d. So even in the limit, we end up getting d. And so in the end, what our equation becomes is ut equals to duxx, which is the tired and true heat equation. So now we have finally derived it, and in the next videos, we will see how to solve it. All right, I hope you like this. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.